All right, so we have spent some time talking about square roots in this class. The next thing that we're going to start taking a look at is basically square roots, but when you have higher powers. So when we're talking about a radical here, so a radical where we're not specifically talking about a square root. Okay, so first let's just talk some vocab so we sort of know what we're talking about. Okay, so we're looking at sort of a square root symbol, right, where you're going to have a number on the inside, but now we're also going to have a little number up here inside of like the little check marky position. Okay, so this number inside of the radical is called the radicand. Okay, so that's your radicand. And the little number up here in the little check marky area is called the index. Okay, so just take a look at these examples and kind of see where that number is meant to be positioned. Okay, so it's sort of like inside of your little check marky part of the problem. You don't put it in the front, okay? And it's definitely not, in the front like a coefficient would be. It's a little tiny number and sort of shoved up there, okay? The way that you would read something like this is you would call it the nth root of x. Okay, so the nth root of x, this would be the third root of -8. This would be the fourth root of 625. Okay, this one would be the third root of 24. Okay, so that's kind of how you read that. Okay, so basically what we're looking at here is it's very, very similar to square roots. Okay, so higher radicals follow the same properties as square roots. So all the same rules that we've kind of looked at before with simplifying. But this time, when you look at a square roots ask you what times itself equals this number. Okay, well, when you look at something with, say, an index number of 3, we're now asking what times itself 3 times equals x. Okay, so the index number is telling you how many times that thing needs to be multiplied by itself. All right, so for example, this guy right here, this is asking us what number times itself 3 times equals 64. Okay, so, well, 4 times 4 times 4 is 64. So the third root of 64 is 4. Okay, this one's asking us what number times itself 3 times equals -8. Now, you may automatically kind of be thinking to yourself, oh, you can't have negatives inside of a square root. It's going to be imaginary. It's not actually, though, right? Because with negatives, when you're going to a third power, that can still work. -2 times -2 times -2 is -8, right? So this is actually going to simplify to just -2. Okay, what number times itself 4 times equals 625? Well, 5. Okay, this one's asking you what number times itself 3 times is equal to -125? Well, that one would be -5. Okay, so that's how you're going to simplify those when they're pretty simple ones. Okay, so then the question comes up, well, what about, say, this guy? I want a number times itself 3 times that equals 24, and there isn't one. Okay, so we're going to have to simplify this another way. So just like simplifying square roots, there are kind of 2 different methods that you can use to simplify higher powers. Okay, so the first method is similar to what a lot of you guys do with square roots. You look at this and you figure out the largest number that's a perfect cube that goes into 24. So here's my little table for reference. Here are my perfect cubes, right? And I'm trying to figure out what's the biggest number in this list that goes into 24. Well, 8. So I could break this into the cube root of 8 times the cube root of 3. The cube root of 8 is 2. And the cube root of 3 doesn't simplify, so that's it. Okay, so that's one method that you can use. All right, now that method is definitely the fastest method, just like it was with square roots. But the problem with it is that you're probably not as familiar with your perfect cubes and your perfect powers of 4 and powers of 5. You're probably not as familiar with those as you are your powers of 2. Okay, so as a backup method, what you can do is use your birthday cake method. So start with 24 and look for prime numbers. So not these guys, right? But prime numbers that evenly go into 24. Primes, remember, are numbers that don't break down any farther. So like 2 goes into 24 12 times, right? And then I'm going to look for another prime that goes into 12. Well, 2 also goes into 12 6 times, right? And then another prime that goes into 6. Well, 2 goes into that 3 times. Prime number that goes into 3 goes in once, and once you get to the top, that's like the candle on your little tiered birthday cake here. And then what we're looking for, when you're looking for square roots, you look for pairs of numbers that go together. Well, here, because my index number is a 3, okay, this is telling me that I'm looking for sets of 3. So here's a set of 3 prime numbers, right? So when I simplify this, write my final answer, the cube root of 2 times 2 times 2 is just 2, and I'm left with this leftover 3. So it gets you to the same spot. It's basically you're just breaking it down so that you can find that number without having to know what the number actually is. Okay, so let's look at another example. So this one, the fourth root of 80. So again, it can be a little bit tricky here. So I'm looking for fourth roots. So I'm looking for my powers of 4, and I need one of these that evenly goes into 80. Well, 16 does. 16 times 5 is 80, which, I don't know, that's not really a multiplication that I would know off the top of my head, but you can break it that way. And then the fourth root of 16 is 2. So this simplifies to 2 times the fourth root of 5. Okay, if we were doing it the other way, then you'd start with 80. And again, I'm just going to divide by prime numbers. So I always start with 2s if they're available, right? So 2 goes into that 40 times. 2 goes into 40 20 times. 2 goes into 20 10 times. 2 goes into 10 5 times. 5 is prime, right? That doesn't break down any farther. So 5 goes into itself once. There's my candle. And in this case, I'm looking for sets of 4 things that match. So here's 4 numbers that match. So this is going to simplify to a 2 on the outside, and then that leftover 5 stays on the inside. Make sure you don't forget your index number. All right, this guy right here. So negative 81, we're taking the cube root of this. So again, I'm trying to think powers of 3, so that's these guys. And I need the largest one of these that goes into 81. Well, 27 would work, okay? Now the thing that we're gonna do that's a little bit different with these guys is because of this negative, right? I can break this into the cube root of 27 times the cube root of 3 times the cube root of negative 1, right? Well, the cube root of 27 is 3. The cube root of 3 just stays the same. And the cube root of negative 1 is just negative 1, right? Negative 1 times negative 1 times negative 1. So I can basically just pull that negative out because it's going to be negative 1 times 3. So anytime you have a cube root, right, and you have a negative in the inside, you can just pull that negative out because you know that there's going to be a negative 1 times itself 3 times in there somewhere. Okay, and if you kind of think about it, that's going to apply anytime you have an odd power, right? Anytime you have an odd index number, it's going to work. Because if there's an odd number of negatives, then that would multiply to a negative, and it's possible. But anytime you have an even index number, you're not going to be able to simplify it. Okay, if this was the fourth power of negative 81, there's no number times itself 4 times that's a negative, right? So that's going to screw you up. And side note, it's not going to equal I. Okay, I is specifically the square root of negative 1. So anytime you have a higher power, it's not going to equal I. If you have a fourth root of negative 1, that's not I. Okay, so it makes things a little bit different as we start looking at that. All right, looking at this one really quick the other way, right? So negative 81, I'm basically going to ignore the negative and just stick with the 81. 2 doesn't go into that, but 3 does, right? And 3 is prime. So 3 goes in there 27 times, 3 goes in there 9 times, 3 goes in there 3 times, 3 goes in there once, and I'm looking for sets of 3. So 3 on the outside, 3 left over on the inside. Don't forget your index number. All right, and then this last one here, this one's pretty easy, right? We have a fifth root, so I know it's okay that there's a negative in there. I can't break down the 6 at all. That's not going to work. But what I can do is I can simplify this by pulling the negative out and leaving it as the fifth root of 6. So that would be the simplified form of that radical. All right, excellent. So one more thing to talk about is solving radical equations. Specifically, we are talking about real solutions here, okay? So we are not dealing with any kind of imaginary or special solutions like that. We're just looking at the ones that are going to be real, okay? If you're taking an even root, you're going to use plus or minus. If you're taking a odd root, you're going to use the same sign as the radicand, all right? And note there are also some imaginary solutions to some of these equations, but we are only finding the real ones. So let's talk about this. We'll go through some examples and you'll kind of see where this comes from. So solving this guy right here, what I'm going to do is I'm going to take the fourth root of both sides. Okay. Now, again, when we were solving these before, right, we would always subtract the 80 from both sides and then solve by factoring, because we know that when you have, say, a cubic equation, right, we talked about how if you had like x cubed equals 27, you would have to subtract that from both sides, because then we know that that's factorable, right? And then from there, you're going to get your two solutions. But here's the thing about doing it this way. This way, you get one real solution, and this would lead you to some imaginary solutions. Okay, well, we are not dealing with imaginary solutions right now. We're strictly dealing with the real ones. So we are going to take the fourth root of both sides. We're acknowledging that there's probably some way that you can get some other answers out of it, just like I just did with this cubic, right? But for right now, we're just worrying about real solutions, okay? So I've got this fourth root of 80. We already simplified this up here, so I'm just going to go ahead and steal that answer. And we're going to get x equals, and then we got 2 times the fourth root of 5. And the only thing that we need to figure out is our sign. So let's think about this for a second. If I'm doing something to the fourth power equaling 80, it could be a positive number to the fourth power that could equal positive 80. But a negative number to the fourth power would also equal positive 80, right? So there's no way for me to tell from this equation whether x was originally positive or negative. So I'm going to list that x would be one of the two, we're not sure which. Okay, so when you have an even root, right, you're taking an even root, you're going to want to include that positive or negative, because if something was raised to an even power, you don't know if it started positive or negative. All right, let's take a look at this guy over here. So this one, we're going to start by isolating that x to the fourth. So I'm going to add the 6 to both sides. Right, and that works out to 64. Okay, I'll divide both sides by 2, so x to the fourth equals 32. And then I'm going to take the fourth power of each side. Okay, so like we just discussed, we know this is going to be positive or negative because there's no way to tell if something to the fourth power was positive or negative to begin with. All right, 32, I'm just going to do a quick birthday cake on that. So 2 goes into that 16 times, 2 goes into that 8 times, 2 goes into that 4 times, 2 goes into that twice, 2 goes into that once. I'm looking for sets of 4. So here's a set of 4. So this is going to simplify to a 2 on the outside and a 2 left on the inside. And there's my solution. All right, and then this last guy down here in the middle. So looking at this guy, just like how we did this when they were squares, we're going to start by dividing both sides by 3 to isolate that power. Then I'm going to take the fifth root of both sides. So fifth root of both sides. Right, so x minus 2 is going to equal, and then here, the fifth root of negative 4, you can pull that negative out. Okay, because you know that there's a negative 1 times 4, and you can take the fourth root of negative, or the fifth root, excuse me, of negative 1. Okay, so then my answer is just going to be 2 minus the fifth root of 4. Not plus or minus, just minus. Okay, and that's how we're finding real solutions. And again, just to reiterate, that doesn't mean that there aren't more solutions, right? There probably are more solutions, but these are the only real solutions.